Okay, so now we're looking at some material out of box B here. We want to take a look at maximum and minimum values on an interval. And what I mean by on an interval here is I've drawn a little sketch of a function here, and I've restricted the domain of this function. Okay, here my domain is, let's see, x is an element of reals, and I've restricted x to go between x equals 3 and x equals 8. So x sort of only exists in this little region right here, such that, okay? And what we're going to see as we go through this is it makes a difference whether or not you've got a restricted domain, how we talk about maximum and minimum values, okay? So I've labeled these points here, and you should have sort of a general idea of what we mean by maximum and minimum values. The key thing that we want to get out of this is what we mean by absolute maximum and minimum, and what we mean by local maximum and minimum. So our absolute maximum here is going to occur at the point 6, 8. Okay? So the absolute maximum is 8 at x equals 6. Okay? Now, why is this the absolute maximum? Because the value, let's just put this in brackets here, f at the function evaluated at x equals 6, or f at 6, is greater than f at x, so the function evaluated at any other x value is greater than f at x for any x, okay, in the domain. Okay? So if I go to any other x values in the domain, I evaluate my function, find out my y value, none of those y values are going to be greater than 8. And you can see that from the graph. Okay? I'm also going to have an absolute minimum. Minimum. And I don't need that dot. Okay? Where's my absolute minimum going to be? Oh, wait, what is the value of the absolute minimum, and where does it occur? Yeah, so the absolute minimum is 2 at x equals 3, okay? Because this is the lowest possible value here that we can have, okay? So again, we can say f at 3 is lower, I should say less than, f at x for any x in my domain. Okay? So the lowest possible value you have here. Now, when I've limited my domain here from 3 to 8, you're always going to have an absolute and a maximum and minimum somewhere. What did I do? Minimum. Thanks. Minimum. Okay, thanks. So let's just say you will have an absolute max and minimum anytime domain is restricted. Okay? Okay. So anytime you say my function begins here and it ends here, you're going to have in that interval some place where you've got a maximum value and a minimum value. Okay? That's not true if we have functions that are defined over the entire real numbers. Nick?
What if it's what if it's a quadratic x to the power of 4 and it touches at the maximum at both ends?
You would have two absolute maxima.
So would they be the, like you would just define them as at X and at X?
Yeah, are both the absolute maximum. Or you would say, let's say it reached up to 10. You would say the absolute maximum is 10 at, and it occurs at 2 points. So you have one maximum value occurring twice. Okay. So that's absolute maximum and absolute minimum. The other one that we have to consider are what are called local maximum, and we'll get to local minimum in a second. So if we look at our graph again here, a local maximum is going to be right here at 4, 6. Okay? And why do we call this a local maximum? Because if we look at sort of the region right around x equals 4 here, some from about here to here, let's say, 6 is the largest value in that little local region here. So it's not the greatest possible value of y, it's just the greatest possible value of y that is close to this value here. Okay? Similarly, if we look at x equals 5 here, and we just look at the little region around x equals 5, we see that 4 is the lowest possible value in there. So this is going to have a local maximum at 4, 6, and a local minimum at, what was this, 5, 4. Okay. Now, the question always arises, what do we do about this 0.32? Is it, this 0.83 over here? It is lower than all of these points that are sort of around it, but it's also an endpoint. Okay, so should we consider this a local maximum or a local minimum? My way of thinking about this is that your endpoints cannot be local max or min, okay, because we don't know what this thing would be doing on the other side here. So your endpoints can be absolute maximum or minimum, but they can't be local maximum or minimum. And this makes more sense as we go on when we look at functions where we haven't restricted the domain for these. But I'm just going to write that as a rule that our endpoints can be absolute maxima and minima, but not local maxima and minima. Okay. So what I've said here is that you're going to have an absolute maximum and minimum anytime you put these limits on your domain. Most of the time we'll be dealing with functions. Let's just give ourselves like a new example here where you haven't restricted the domain. So for instance, let's say we had the function y equals x squared. Okay. And if we're looking for an absolute max and an absolute min, well, does this have an absolute minimum value?
Yes.
Nick? Yeah, it does at 0, 0. Because this is, or I guess I haven't drawn this as 0, 0. Let's say this is at 0, 1. Okay? Because that's the lowest possible value it's going to reach. Does this have an absolute maximum value? Yeah. It goes off to infinity in both directions. So this does not have an absolute maximum. Okay? So it's possible for it to have an absolute minimum, no absolute maximum. In this case, this point, 0, 1, would also be a local minimum. Okay? Because it's lower than all the points right around it. So it's both an absolute minimum and a local minimum. And if we were looking for local max, local maximum, well, we don't have any maxima in there either. Okay, we don't have anywhere in that curve here that are bigger than anything else. So we could take a look at the example that Nick was asking about earlier, where we had something that went like this. Okay? And we could ask ourselves, do we have, do we have a local maximum? Well, sorry, do we have an absolute maximum? Yes, we have an absolute max that occurs in 2 places. Those 2 points are also local maximum. Okay? And down in here, we've got a local minima, but we have no absolute minimum.
Does that mean for like the first example where the absolute maximum was 8 when x equals 6, is that also a local maximum then?
Yeah, I guess you could say that is also a local maximum.
So
Yeah,
you think this would be much more than it is?
yeah, it would be. Richard?
What do you count as the area of local? Just the region.
Just right around it. You can, mathematically, you can make that region arbitrarily small. Because if you go, you can make it as small as you want, and it's still going to be the maximum. Like, okay. So it's, yeah. I mean, yeah, we don't have to worry about the mathematical definition in here. You just have to recognize that, hey, that's sort of the maximum point. Now, what I was saying earlier about if we restrict the domain, let's say I said that this thing is only defined for, let's say, x is between 10 and negative 10. So I said we're going to just chop this thing off here and here. Then all of a sudden, I would have an absolute minimum because I've got my endpoints. Okay? Okay, then I'll say would have an absolute min. Okay? So that's absolute maximum minimum. All right. Where am I going from here? So, finding maximum and minimum values. This stuff here is, I think it's straight out of the textbook, so don't worry about copying this down. The idea here is, if I've got a maximum here, a local maximum, and local minimum down here, what do I notice is special about these points here? Well, we've already talked about, you guys have mentioned that these are turning points where it changes direction. We also notice that at these points, if we were to draw in our tangents, the slope of the tangent would be 0. Here and here. Okay? So this suggests to us a way of looking for these turning points or these local maxima and min. And I wrote max there, and I should have written min. Okay. And your textbook calls this Fermat's theorem, that if f has a local maximum or minimum at some point, x equals c, then the derivative at c equals 0, or the derivative does not exist at this point. This is just a way of saying that everywhere that there is a turning point, or a local maximum and minimum, your derivative is going to be 0.
So what happens if we have like an asymptote?
Okay? It doesn't tell you that everywhere the maximum and minimum, everywhere that the derivative is 0, there's a maximum minimum.
Does not exist, so if the derivative does not exist at that point.
If it does not exist, there could be a maximum or minimum there. It doesn't say that there necessarily is one. Okay? So everywhere that the derivative is, everywhere that there is a turning point, the derivative will be 0. But everywhere that the derivative is 0, there doesn't necessarily have to be a turning point. Okay? So all this suggests is a way that you can go about looking for turning points, which is looking for where the derivative is equal to 0. Okay? And that's how we're going to find them. And we're going to use a thing called the first derivative test, okay? And this is sort of the big thing that you want to be able to use out of this whole thing here. So let C be a critical number of a function f at x. What do we mean by a critical number? A critical number is just a point where the derivative equals 0, okay? Because from that definition on the previous page, those are possible places where the derivative equals 0. Okay? Those are possible places where we have a turning point, sorry. So f prime equals 0 at a critical number. Okay. Now, let's say we found out this point C, where the derivative is equal to 0. There are three possibilities. We can have a local maximum, we can have a local minimum, or it can be one of these special cases where it's not a local maximum or minimum. And we want to figure out which of these things it is. And the way we're going to do this is we're going to look at, as the name suggests, we're going to look at the sign, we're going to look at what the value of the first derivative is. So our first possibility is at this point C, if the derivative, okay, f prime at x, changes from negative to positive, okay, then let's call this C, f at C, which is just the point, is a local minimum. Okay. So you can visualize this. Let's say you've got some curve like this. In the middle is C. On one side of it, slope of the tangent is negative. On the other side, slope of the tangent is positive. Right at C, the slope of the tangent is 0. So this is clearly a local minimum. Well, I think you can see what the next case is going to be. If f prime at x changes from positive to negative, at C, then this point is a local max. Because then we would have point C like this. On one side, our derivative, or the slope of the tangent, is positive. Over here, the slope of the tangent is negative. At C again, the slope of the tangent is 0. So this is clearly a local maximum. Now, it's possible that at point C, the sign of the derivative, or the slope of the tangent, doesn't change sign at all. That's our third possibility. If f prime at x does not change sign at C, in this point, then what do I want to say here? I want to say the point C, f at C, is not a local max or min. Okay. And the most common case is, you can imagine a curve that goes like this, like y equals x cubed. At this point right here, the slope of the tangent is 0. But if we look on either side of that point, the slope of the tangent hasn't changed. Okay? So this is actually what we call a point of inflection. But there can be other reasons why you can get a critical number where the derivative is 0 or does not exist, but the slope of the tangent doesn't change sign. Okay? So this is the way you want to find a local maximum or minimum. You want to find the critical numbers, and you want to see what the sign is, or what the slope of the tangent is on either side of it. Okay? So let's take a look at an example here. Find the critical numbers for f at x equals x cubed minus 12x, then find the maximum and minimum values of f at x on the interval -3 to 5. So let's first find our critical numbers. Okay. So, critical numbers. We want to take our derivative, and we want to set it equal to 0. And we want to solve for x. So what can I do here? I can factor out 3. And then I can factor this difference of squares. This is telling me that my critical numbers are x equals +2 and -2. That's the first part. Now, when I'm looking for maxima and minima, I should consider these two critical numbers, +1 and +2 and -2, and I should also take a look at my two endpoints. So let's just say we're also going to look at the endpoints x equals -3 and 5. I want to find out if these two critical numbers represent local max, local maximum, or local minimum. Okay. So we can do that by checking the sign of the derivative on either side of these things. So we can set up our intervals here. We've got one interval that's going to go from, let's see, -3 to -2. Our next interval goes from -2 to +2. Then we have an interval that goes from, what, +2 to 5. And we want to check the sign of each of our terms here in our first derivative. So we are checking sign of f prime. All right, so the 3 is going to be positive no matter what. X minus 2 is going to be, let's see, negative, positive, correct? Richard's nodding hesitantly, okay. And then x plus 2 is going to be, let's see, negative, positive, positive. Okay, so our derivative then is going to be positive, negative, positive. So what does this tell us? Well, this tells us that we have a, let's see, it goes from positive to negative to positive. So we have a local maximum at x equals -2. We have a local minimum at x equals +2. Okay? Because at -2 it goes from positive to negative, and at +2 it goes from negative to positive. We should work out these values as well, the value of the function at -2 and 2. Because the next thing we need to check for is check for absolute maximum and minimum. Okay. We know we have to do this because, again, because I restricted the domain here. So we're going to have an absolute maximum and minimum. So we need to find out where it is. So this is a possible absolute maximum. This is a possible absolute minimum. And the way we can just check is we check what the y values are. So f at -2 is 16. F at +2, we work that out. It's -16. We also need to check our endpoints as well. So f at -3 and f at 5. So f at -3 is 9, and f at 5 is 65. So we've got local maximum here, a local minimum here. Do we have, well, we have to have an absolute maximum and min. So what is our absolute maximum? It's going to be 65 at x equals 9. That's this point right here. And what is our absolute minimum? At x equals, yeah, thank you. I wrote 9. I meant 5. What is our absolute minimum going to be? Yeah, it's the same as our local minimum. So our absolute minimum is -16 at x equals 2. Okay. Okay. So there we've used first derivative test to find our local maximum and our local minimum, and then we also checked the endpoints to figure out where our absolute maximum and minimum were. Okay. I want to do one more example here. Okay. Maybe you guys can explain to me how we do this one. Find the local maximum and minimum of y equals 1/4 x to the 4th minus 2x cubed. Right? And I'm just going to... Okay, let's try this question here. What are we going to do first? Take the derivative and set it equal to 0, and then factor, because what are we looking for when we do that? Not the turning points, and critical numbers. So to find our critical numbers, we're going to take our derivative, which is going to be x cubed minus 6x squared. We're going to set it equal to 0, and we're going to solve for x by factoring. So what can I factor out here? I can common factor out x squared, and I will get x minus 6. From this, what are my critical numbers? Nick? 6 and 0. So x equals 6 and 0 are my critical numbers. So to find out whether these critical numbers represent local maxima, local minima, or something else, and we'll try spelling numbers correctly this time, we are going to set up our little table here. So intervals that we're going to have are going to be, what are my intervals going to be here?
Wait, you don't have a domain, right? So
Yeah. Okay, good. Right, okay. And as Nick said, we don't have a restriction on our domain, so we don't have to check the endpoints for absolute maximum or minimum. Okay. So we want to check the sign of each of our terms here and figure out overall the sign of our derivative. Okay. X squared is pretty easy. It's going to be positive no matter what we put in there. X minus 6 is going to be, I'm thinking negative, negative, positive. Good. Okay. And so our derivative is going to be negative, negative, positive. So if we visualize this, f primed is negative. It's going to be decreasing. Slope of the tangent is going to be negative. Slope of the tangent is going to be negative here. And over here, the slope of the tangent is going to be positive. So what can we figure out? What can we say about local max and min here? Nick.
Local min is 6.
Okay. X equals 6. Okay. And what about x equals 0?
It's not a,
Yeah. X equals 0 is neither a local maximum nor a local min. So we've got just that one local minimum here. Now, if we were to think about absolute maxima and minima, what can we say here? What kind of function do we have here? Cubic. So what does the end behavior have to be like? Same or opposite? Oh, sorry. I was pointing at our derivative there. We want to go back to the original function though, right? It's quartic, yeah, so it's got to have, end behavior's got to be the same. So it's a quartic function. End behavior is the same. So what does that tell us about our local minimum? I mean, if we've got a local minimum here, and our end behavior has to be the same, this local minimum is also our absolute minimum, okay? So we can say this is also an absolute minimum. Okay?
do you have to evaluate for the y value?
We probably should. We should figure out, we should do, find the local maximum. Yeah, I think it's enough in this one that we know where the minimum occurs. Okay, we can, and the reason we evaluated in the previous one was to check and see which one was our absolute and which one was our local. Okay, we don't need to do that here. So if we were to sketch a graph of this thing, it would look like this. With our local minimum at x equals 6 and a point of inflection at x equals 0, the OI. Okay? So the idea is the only way to check for sure if this is a local minimum or a local maximum or something else is check the derivative, the sign of the derivative on either side of the critical number. And that's where we're going to